Hi, my name's Bob Flynn, founder of Exacta Global Smart Solutions. In this session, during Etsy IoT Week, I'm going to demonstrate some of the semantic features of OneMDM that I described in the previous session. While I will describe everything to you that you need to follow along in this session, there's more detail available in the first session, as well as descriptions of other semantic capabilities of OneMDM. For this demonstration, I'll be using the coordinate platform for the OneMDM CSE. For sending specific requests, I'll be using Postman. So first we need to describe our device. I am providing a description of the smart lamppost. In this description that will go into the payload of a semantic descriptor resource, I'm describing what the device is. It's a lamppost and a photometer, which is why we're calling it a smart lamppost. I'm describing what it does. It measures the properties of illuminance, luminescence, and phosphorescence. I'm describing where it is. It's at the latitude and longitude shown here, and it's also located on Gran Via Street in Madrid. And then I'm also providing some other useful information: the manufacturer, the last maintenance date, and properties of the light. This table shows all the devices that I'll have in this demonstration. We will refer to this table several times. So let me describe the complete scenario. Each device is modeled as an application entity, or AE resource. One of the attributes is the app ID, which is an identifier of the application. That's a mandatory attribute, so you'll see that in all the requests. Likewise with the request reachability, which indicates that the device can receive requests. There's a labels attribute that I'm providing for some of the devices in here, and these are used for the native one-end-to-end discovery requests. And I'm going to talk a little bit more about that later on as well. And then there's an access control policy IDs attribute, which is used to determine access to this resource. You'll see how this becomes important later as well. And then the semantic descriptor resource, which is a child resource of the AE, and that is what contains the semantic annotation that I'll be describing that I showed you in the previous slide. So like I said, each device is modeled as an application entity, or an AE, and each device is annotated with a semantic description of the device, and then access control policies are defined for each of the resources. A control application has permissions to discover these resources. There's a second application that does not have permissions. So I'm going to show some of the typical primitives before I get into the live demonstration. So this is what a typical AE resource looks like. And what you see here is, in the request headers, the origin attribute of the request is the entity ID of the device itself. In this case, it's CGV1. The content type changes for the type of resource. In this case, it's an application or AE resource, so it's TY equals 2. And then a request identifier is it's a mandatory attribute of one-end-to-end. For the body of the payload, you'll see the application identifier that I mentioned before. That's not really used in this demonstration. However, it's a required attribute, so I have a value in there. And then I put a label in there. Again, this label is used for native one-end-to-end discovery. And I put the location of the device as an example here for the label, and I'll talk about that a little bit more also. I also identify the access control policy ID. This is the ID of the access control policy resource that will govern access to this resource. A little bit about the access control policy resource. Again, on the left, what we see is the type has to change because it's an access control policy resource which has type 1, and the originator of the request is the control application. And what you'll see in the body of the access control policy resource is that I give both the device itself, CGV1 in this case, full access, and I also give AE01 full access to everything involved with this particular permission. So any resource that I give this ACP ID to will have these permissions. And then for the semantic descriptor primitive resource, again, the resource type changes. So that's a TY24. And the origin of this I have as the device itself. So in this case, it's the CGV1. And to the right, you'll see the payload, which, as we described before, has the binary 64 or the base 64 encoded semantic description. And also, I'm showing that it has the access control policy ID of ACP1. So now that I have described all the resources, let's go ahead and create them. So first I'm going to start with the control application and the access control policies associated with that. So first I'm going to create the access control policy resource for the control app, and then the control application itself. And then this is a semantic descriptor related to the control application, and I'll talk about that a little bit later when I go through some of the queries. And then I'm going to create a second application that I'll do a query from as well. However, what we'll see is that this application does not have permissions on the semantic descriptor resources that I'll be creating for my devices, and that will become significant. So this is the access control policy for the first device, and then the application entity resource for the first device, and the semantic descriptor resource for the first device. And we can see in the results from each of the queries that the status is created, or the resource is created, so everything is coming out fine. So we'll go ahead and just repeat this for all of the devices. I'm just checking to make sure that the status is created for each one of these. coming to the end. And the last device. Okay, so now that I have all the devices created, I can go ahead and start executing some of the queries. And so the first query I'm going to do is I'm just going to find the street lights on Grand Via Street. Okay, and as we saw in the semantic descriptors and the table that we had, there are 2 lights that are on Grand Via Street. And the originator of this request is the CAE01, which is my control application. So when I hit send, I'm expecting those two lampposts to come back, lamppost GV1 and lamppost GV2, which matches what we described in our setup. Okay, so as a second query, I'm going to use labels this time. And so this is not using semantics. This is using the 1M to M labels and the 1M to M discovery procedures to perform these queries. And I put a label in all 3 of these devices indicating their location. I only did it for the devices on Grand Via for this particular example. So, but what we'll see is I'm issuing a 1M to M discovery request for the resources that have Grand Via as one of the label attributes. And I find my 3 devices, the same 2 from before, the lamppost and the photometer. Okay, so and what I'm trying to point out here is that 1M to M has some basic discovery capabilities, even without semantics. But what we're going to see through the next set of queries is that the querying capability that is enabled by using semantics is very powerful and probably even necessary, because I think what we'll see with some of these queries is using labels becomes a scalability problem and is probably not very scalable. But before we talk about that, I'm going to do a query from where the originator is AE2. And if you recall what I described, the access control policies that we're giving to all the semantic descriptor resources were only for the devices themselves and for the control app, which was CAE01. So when I do a query coming from the originator of CAE2, I'm expecting to get no results back, which is what I'm getting here. This is an empty URI list. So there are no devices that are discovered because this particular application does not have permissions. So now I'm going to go into another query, and this is where we're going to start seeing the power in the semantic queries, because the query that I'm going to issue is I'm going to be searching for sensors within a neighborhood called Seoul. And from what we saw, what I described earlier, I didn't in any of the semantic descriptors, I did not put the term serif sensor. I put these serif extension terminology, and this is a photometer. And likewise, I did not describe anything with regard to the neighborhood of Seoul. I just put the street that they're on. And that was true for all of these devices. However, what I did do was in the semantic descriptor of that control app, AE01, I did provide a description in the semantic descriptor of just that single application, that single originator, AE01, the control app. And in that control app's semantic descriptor, I described this neighborhood named Seoul, and I said that this neighborhood Seoul contains the streets Grand Via and Montera. Also, what I have enabled in the semantics is the full ontology, the full serif ontologies. So even though none of my semantic descriptors specifically use the terms serif sensor, using Sparkle queries and the capabilities that come along with that, by using the inheritance of the serif sensor model, the fact that this is derived from a serif sensor means that when I issue a query for serif sensor, all of my extensions that are derived from that will also be found. So let's take a look at that in the query. So that is this query, and I'm saying, is this query, and here I'm saying, let's find the sensor devices that belong to the Seoul neighborhood. I'm going to issue that request, and I've get three devices, the lamppost and 2 photometers, lamppost GV1, photometer G1, and photometer M1. So let's go back and take a look at our table to see what's happening there. And again, Seoul contains the streets Grand Via and Montera. So we'll see Grand Via and Montera, and we're getting these 2 photometers, G1 and M1, and we also get lamppost GV1 because it's what we defined as a smart lamppost, which also includes a meter, which is a sensor in the serif ontology. So because of our use of our semantic descriptors, we're able to define more general queries and get much better results. Now, if we were to try to do this using the labels that are defined in the base 1M to M functionality, what we would have to do is go through all those resources and update the label attributes of those devices. For example, right here, I would have to update this device and also include Seoul. And I would actually also have to include things like the fact that it's a sensor, as opposed to just a light meter. And what we see is this really becomes not very scalable. For every type of variation on those requests, having to go back and update all the particular devices or resources that have that particular label becomes unmanageable. Whereas the fact that I was able to do that with just adding another set of triples to the control app that was issuing this request, it was able to apply these new definitions to the devices that have already existed. That's a pretty powerful and useful function in the Internet of Things and devices when we talk about the scales that will be out there for these kinds of devices. So let's take a look at a couple other types of queries that can be issued using semantics that are not quite so easy to do with the standard one M-to-M queries. And in this particular query, I'm just looking for, this is more of going back to the basic type of query. I am looking for sensors that measure the illuminance value. So that, this comes back to, if we go back to our table, we're looking for sensors, and I got this lamppost GV1, the lamppost T2, and the photometer M1 and photometer G1. And if I look at my illuminance, again, I'll see those same devices identified there.
Your phone is not connected to a Wi-Fi network, so I can't help you with that at the moment.
So in this next query, I'm going to start taking advantage of some of the query capabilities of the Sparkle query language. And what this one is doing is, well, I'll execute it first and then I'll explain it. So what you'll see here is I issued a query, and the query was to find the number of devices in each street that belong to the Seoul neighborhood. So the Seoul neighborhood, again, was Montera and Grand Via. And it's given me a count of three devices in Montera and 3 devices in Grand Via. And if we just go back to our table and check that, we have our 3 devices in Grand Via and 3 devices in Montera. So what did we do? What did we do for this query? In this case, we started off with some instructions to tell it to return a count rather than just a discovery type of resource ID. So I'm counting the number of devices and returning it as a number of devices. And I'm also, listing the streets. So it's for each street, I'm counting the number of devices. And where I'm asking for the number of devices, I'm defining that as a serif device. So compared to the previous one where I did a serif sensor, this time I'm using a serif device, and a serif sensor it inherits from the serif device, which is why in this case we got both lights and photometers. So in the next query, this is a find streets that do not have any sensors on them. And in this case, that's Fuen Carroll. And Fuen Carroll has lights but no meter. So, but all the other streets in our scenario have sensors on them. And again, we were able to do that through the expressive Sparkle query language, where we're saying return the street, where it doesn't exist, where it does not exist a street containing that sensor, or containing a serif sensor. For a next query, find the properties measured by the sensors on Grand Via Street. So this lists the different properties of the sensors. And again, the lamp post is a smart post. It has a sensor in it, and then also photometer G1. So we're getting the luminescence, and light absorption, and luminance, luminescence, and phosphorescence for each of those devices. And as before, it matches our table. Right, here's the 3 for GV1, and then for this was on Montero Street, I believe, or for G1. For G1, it was these three: light absorption, luminescence, and illuminance. And again, looking at the query for that, the point here is that for the Sparkle query, we can have it return various information from the content of the semantic descriptors that were provided. And then as a last query, I'm looking for streets containing smart objects, where a smart object is a device that has both a light and a meter. Well, actually, it's a device and a sensor at the same time, not necessarily a light and a meter. And if we go back to our table, GV1, T2, and M1, GV1, T2, and M1, these are the devices that are both a light and a meter. And we were able to do that through the use of our Sparkle queries. The key takeaway on all of this is the amazing and powerful and expressive queries that we can issue using Sparkle queries. That's great and that's nice, but what's even more powerful is the fact that we can add these triples to particular devices or entities, and these can be propagated and applied to information in other semantic descriptors without having to go back and update those other devices in semantic descriptors. And that can create, that makes us extremely powerful, and it's also how we can achieve interoperability with a variety of different ontologies, because we can start using the capabilities that are defined by Sparkle and the ontologies, things like same as and equivalency, and put them into triples, and then be able to issue queries based on the terminology that we know. And that, if we use the one end-to-end base ontology as that example, we'll be able to issue queries on based on the one end-to-end ontology. And if a new ontology is entered, as long as we define the relationship between those ontologies, the queries will still work. And that brings a lot of additional value to the capabilities that one end-to-end offers. So again, my name is Bob Flynn, the founder of Exacta Global Smart Solutions. I'm also the vice chair of the TDE working group in 1M2M, and you can reach me from my website or from my LinkedIn page. And if you're looking for more information about the core implementation of 1M2M, you can reach out to Shaquille at the contact information shown here.